found this book online. It's in Canvas under textbook. And so this is going to be a lecture from the second lecture from this sequence, and I'm going to cover part of this book. This book is from MIT. It's a very top-level book on algorithms, so I'll cover some of their material in this course. And today is going to be our first. We're going to try to tie in some of the things that we've been doing and just continue with it. You ready to go? You going already?
Yes.
Ha! What a guy. Okay, so this just tells you kind of what we're going to be talking about. We're going to be looking at, we already know about big O, big theta, and big omega notation. We know all this stuff. We're going to look at iterating the recurrence, a recursion tree method, and also a very important algorithm called the master method or the master algorithm, and when it's applicable and how to work it. All right, so first of all, this is the big O notation. Big O notation is upper bound notation. I told you before that if you want to evaluate big O, we typically do it by limits. But there's also another way of looking at it without limits, and that is you could say that f of n is an element of the set big O of g of n if there exists constants c, which is a positive constant, and some value for n, some starting value for n, we'll call it n naught, so that if n is bigger than this n naught, then the function of n will be bounded by less than or equal to this constant times g of n for all values of n from n naught and onwards. It means that this function f of n will be less than or equal to cg of n beyond the point n naught and forever, as long as we use the appropriate constant. So that means that this is going to be less than or equal to all the time. So this is an upper bound. So you can certainly imagine that if f of n and g of n are both quadratic, then of course if the function of n has 3n squared, then we can always add here as a constant 4. Why? Because 4 is bigger than 3. Well, what if this has a bigger linear constant? Then we'll use n naught a little bit further down the line so that we have this proper relationship. Does that make sense? So this is, you might have seen this before in a more elementary approach to big O. But it's still essentially the same thing. It basically means it's less than or equal to, which means it is less than or equal to, exactly less than or equal to, or it is actually a slower growing function, less than or equal to. But for smaller values, where n is less than n naught, it's possible that this relationship doesn't hold. We only have it required to hold for large values of n, and those n values specifically beyond some starting value of n and going larger. So for example, we can say 2n squared rather is an element of big O of n cubed. Now you can see that this is true as long as c is equal to 1, so it's going to be 1 times n cubed, n naught is equal to 2. So what is the value of, what is the smallest value of n that's greater than or equal to n naught? 2. So what's 2 to the third? 8. And what is 2 times 2 squared? 8. So what do we have here? We have equality. But now what happens as we go beyond n naught? Like we'll go to 3. When we go to 3, what's 3 to the third? 27. And this is going to be? It's going to be 18. So that you can see now it's less than. And of course, you recognize the fact that the cubic function is growing more quickly. It will continue being less than. But there may be some small values for which it is not true. For example, if you go less than n naught, like at 1, if n is equal to 1, this is 1 cubed, and this is 2 times 1 squared. Well, 2, is it less than or equal to 1? No. So that's a value that we can ignore. We'll start at this starting value. So once you reach 2, then we have the relationship less than or equal to with g of n being multiplied by a constant. Okay, what if I had a value, for example, here, instead of 2n squared, but 10n squared? So again, what we would have to do is do what? To show it.
The starting value.
Our starting value n naught may be a little bit bigger, or maybe the constant would be a little bit bigger, or a combination of those things. I could ask you a question like, fine, if this is 10n squared is an element of big O of n cubed, I might say find the smallest integer value of c, n and naught, that produce this relationship. Okay? So at that point, you'd have to think about what you have to do. Well, the smallest value of c, what do you think that would be? It would be 1. And the reason is because this function eventually will overtake the other one, so all we have to do is use the c value of 1 and then use an n value high enough. Okay. But remember, even though 2n squared is big O of n cubed, it is also little o of n cubed. Because little o means that it's always less than beyond a certain value. Okay.
Can the n naught or c can be decimal or 0.1 or something?
No. Yes, they can be. They can be, actually. They can be. But that's why I said we choose an integer value, because then you're limited in choosing integers. Of course, if you chose, for example, 0.5 for this, then n naught would have to be higher. That's all. All right, so you get the idea here. So I'm not going to spend too much time. So I don't know why, because now this is the way I would say 2n squared is an element of big O of n cubed. How about 2n cubed? Is 2n cubed an element of big O of n cubed? Yes. For which constant? What would the constant have to be? The constant could be as low as
1.
Oh, 2.
Now I forgot my question. What was my question? 2n cubed. 2n cubed element of O n cubed.
Yes, constant should be 1.
What would the constant have to be?
1.
No.
Less equals.
It would have to be anything larger than 2. Because if you have 2n cubed, then 2n cubed can never beat it. Well, I guess it could be 2n cubed if you use equality. Absolutely, yes. I'm going to say 2 is fine. But it cannot be lower than 2. So it has to be 2 or higher. Absolutely. Good. All right. We can skip this part here. This is the equivalent of the other notation, where the function is basically greater than or equal to Cg of n for all n. So basically it means this is a lower bound. That means that this is bigger than or equal to this thing. Okay. So I'm not going to spend too much time on that. You can see here that the theta of g of n is equal to big O of g of n intersect big omega of g of n. Does that make sense? These are functions that grow what? No faster than g. These are functions that grow no slower than g. So these are functions that grow proportional to g. Okay? Okay, and we talked about the little o and the omega, so I'm going to skip those, so I think we're fine. All right, so we're going to skip the substitution method. We're going to go to another method. Skip. Okay. We're going to look at a really cool method called the recursion tree method, which can help us solve kind of graphically, so we can visualize what's going on in terms of complexity. So a recursion tree models the costs of a recursive execution of an algorithm, and so what we do is, as the recursion tree is building, you start with a root, and then you explode the tree to each new level, and then you try to see a pattern, and eventually, as you model the recursive tree, you get to the bottom of the tree. And then you stop. And then by visually looking at the tree and attributing the costs to each level and to each of the nodes within the tree, you can find out the complexity of the algorithm. Okay? So we'll see how that works. So, for example, let's say we have T of n is our complexity of our algorithm is T of n over 4 plus T of n over 2 plus n squared. Okay, let's make sure we are clear on what each of these things are. What do we call, what is this part referring to in terms of cost? This is the what cost?
1/4 of
Huh?
T
Say
n.
what you said. Recursive cost. This is the recursive cost. Why? Because it's the T of n is now equal to another T. So it's recursive cost because it's the recursion, so it's a recursive cost. Now what about t of n over 2? That's also a recursive cost. So n squared is not a function of t, therefore n squared is the what? Anybody know? Is the actual cost. Actual cost. So now the question is, actual cost of what? It's the actual cost of the incoming parameter into the function at its given recursive level. Whoa, what does that mean? It means that when we have a function, do you understand what this function would look like? If you had to do a funny function, just like write a fake C++ function that has this complexity. Do you know how to do it? So the function is called funny, and the parameter is n. So how does this function look? How does this math translate to code? What would a code like this look like? The answer is easy. If the function is called funny, and the parameter coming in is n, then the body of the function has another call to funny with n over 4. Then it has another call to funny with n over 2, and then it has to have an actual cost of n squared. How do you get a cost of n squared? How do you get a cost of n squared? Loop within a loop. So you have a loop from 1 to n, and inside of it, loop from 1 to n, and then a statement. Well, that statement is going to execute how many times? N squared. That's the actual cost. Now, that's what happens when the parameter coming in is n. What happens if the parameter coming in is n over 3? If it's coming to n over 3, then this will be what? Funny with a parameter of n over 12. How about this one? Then the next one will be funny of 6, and this would be n over 3 cubed. Does that make sense? So depending upon the incoming parameter, the recurrent costs and the actual cost will be a function of that incoming parameter. You simply substitute into n whatever was the value of the incoming parameter. Scott?
So wait, if n was 3?
I didn't say 3. N over 3.
Oh, n over 3.
So if it was n over 3, this would be n over 3 over 4.
Gotcha.
That would be n over 12. And then n over 3 over 2, n over 12. And this would be n over 3 squared. You got the idea. So therefore, we are now going to talk about recursive levels. Recursive levels are the levels of the recursion tree, which are also the levels of a tree. And so therefore, think of this t of n as the root. The root what? The root cost. So t of n is the cost of the algorithm, correct? Therefore, as the tree expands, the cost of the algorithm will be the cost of the tree. So right now, it's t of n. So therefore, notice that we call this recursive level 0. And the reason we'll call it recursive level 0 is because this cost of this recurrence applies to this algorithm, this fake algorithm that we talked about. This is the algorithm. N comes in, we recurse with n over 4, we recurse with n over 2, and then we have a n by n loop. That's what the algorithm looks like, actually, right? So therefore, or it could have, the loop could start, then you recurse, then you recurse. I don't care. Or you can recurse, loop, loop, recurse again. It doesn't matter. All of them are the same complexity. So what's going to happen is, this is recursive level 0. This is the outside function sending in n as a parameter to level 0. How much actual work is going to happen at level 0? How much actual work will be done at this level? This is level 0. Well, this is the cost of the algorithm, right? Mm-hmm. So therefore, what are you passing into level 0? N. That's the coming into this n. So therefore, how much actual work will be done at level 0? N squared. That's the actual work. And then what you're going to do is you're going to then recurse with quarter of the work and recurse again with half of the work. But those recursions are going to be calls to the same function from level 0. They're going to be level 1. And they will also have actual costs and recurrent costs. So as we expand this tree, we replace level 0 and the incoming parameter with its actual work. And actual work is n squared, and then we send to level 1 and another level 1, the quarter and the 2. So now, what we're going to get is we're going to get n over 4, right? Coming in. to level 1, left recursion if you will, and n over 2 coming into the right recursion. Now let's see what's going to happen. Let's look at the left branch, level 1. n over 4 is coming in. So now think of n over 4 replacing n. How much actual work is going to happen at this left branch of level 1?
N over 4 squared.
N over 4 quantity squared. So it's going to be n over 4 squared. So it's going to be n squared over 16. And on the right side, actual work will be?
N squared over 4.
Okay. So those will be the actual work. And then this, again, will send 2 branches down, recursing again. This is going to be a quarter of n over 4, which is n over 16. And this is going to be n over 8. And this is going to be n over 8. And this is going to be n over 4. So it's going to be n over 16, n over 8, n over 8, n over 4. Those are going to be the recurrent costs. But the actual costs, n squared over 16, n squared over 4. Scott?
So the actual cost is it per each level?
Per level.
So are those the actual costs like added together for each child, or?
Yeah, I mean, what's going to happen is on a single CPU machine, and typically you're executing sequentially, you're going to execute this cost first. Let me go to the next level here, so you can see what's going to happen here, right? So this is going to be n squared over 16, n squared over 4. So you're going to pay those costs. I don't know if you're going to pay them boom, boom, or you're going to pay it boom, boom, like this, and then come back and then pay those costs. You're going to pay those costs.
Okay.
But we're focusing on them level 0, level 1, here comes level 2. So now you can see what's going to happen is, when we're at level 2, we have 4 instances of the recurrence. So again, n over 16 replaces n over 16 squared. This is going to be n squared over 256. Notice that the divisor over the square is growing exponentially by n squared over 1, n squared over 4, n squared over 256. So it's growing what? Exponentially by? By 4. Divide by 4, divide by 4, right? And squared. So it's going to be by 1, by 16, I would say. Right? By 16. Because this is going to be n over 256. So it's growing exponentially by 16. Correct. So now we're going to go to the next level, and you can see it's going to be n over 6. So this is n over 256, n over 64, n over 64, n over 16, etc. Now, n is what? N is just the input size of the algorithm. It's the size of the problem we're solving. And so what are we doing with this problem? We're cutting it into 4 pieces, into quarters, cutting into halves this way. Now, when we cut something into quarters, how many times can we cut it into quarters? How many times can I cut something into quarters? So, for example, if I have something that's 16, I cut it into quarters. Each quarter is what? 4. Now I take 4 and I cut into quarters. What do I have? 1. Well, once I cut something into from 16 to 4, then to 1, 1 means what? The size of the problem is 1. Okay? So that means I'm done cutting it. We can't cut it any smaller than that because we don't solve fractional problems of fractional sizes. The size of the problem is reduced from a large number down to unity. When we're down to unity, we're solving a problem of size 1. So therefore, you can see that eventually, if we follow left, 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 always, what will be the height of the tree? That's another way of saying, when will the actual work go to unity?
N over n?
Look at this. N over 1, n over 4, n over 16. What's the next one?
256.
N over 64. N over 128, what will be the height of the most left branch? The answer is log base 4 of n. Base 4. Okay. Okay, so log base 4. Because how many times can you cut something into a quarter? Log base 4. How many times can you cut something in half? Log base 2. Think about it. You got 16. So you're going to cut it in half. 8, 4, 2, 1. So 16 you can only cut in half 4 times. 32. You cut once, 16, 8, 4, 2, 1. 5 times. So you can only cut something in half log base 2 number of times. You can only cut something into quarters log base 4 number of times. So notice that this left branch, the height of this branch, if I go from here to here, will be approximately equal to log base 4 of n. Agreed? Okay, now if you look at the very rightmost branch, notice the problem size is n over 2, n over 4, n over 8, n over 16, n over 32. This problem is getting cut in half, in half, in half. So therefore, the height of this branch will be what? Log base 2. Now, which number is a bigger number? Log base 4 or log base 2? Log base 2 is a bigger number. Log base 4 is a smaller number. What's going to happen is the tree will go to unity quickly here and slowly here. It's still very fast on this side. It's still logarithmic with respect to base 2, but here it's logarithmic with respect to base 4. So this will be shorter. This will be longer. Now what about that's the outside. What about on the inside? On the inside, this tree is going to look like this. You understand? It's going to be a jagged tree going down to here. So we can sort of make the following observation. This tree will go to unity fastest here, slowest here, and then in here it will sort of progress and match up to here. It will sort of be one of these jagged thingies that go into here until it gets to here. So therefore, if I make an assumption that if I go all the way down here, and I pretend the tree is actually, you know what a full tree is? Full. That means it's completely full. That means it goes all the way up and all the way down. Everywhere it's full. Our tree is not going to be full. It's going to be a little bit skewed. It's going to be a little bit like this, right? Like that. I don't know. So what's going to happen is if we assume the tree is actually full, then we can calculate if we add the actual work here and the actual work here and the actual here and keep adding it until we get to the level here. Even though there's no level here, but we assume there is, we can still get a pretty good approximation for the total amount of work of this algorithm if we just add up all the work across all the levels recursively. So that's what we're going to do. And when we do that, you see that level 0 has exactly n squared work. Duh. Easy. I know that. Okay? Now this one is going to have really n squared over 16 plus n squared over 4. So it's going to go into 16ths, and what we get is 5/16 n squared. And when we go to level 2, 0, 1, 2, you probably can't do that one in your head. We get 25 over 256 n squared. Now that might look kind of bizarre, but actually it's extremely beautiful pattern. And the pattern is 5 over 16. If you look at 5/16 and 25 over 256, you realize that to go from here to here, you are just squaring it. And if you go from here to here, you are just squaring it. So what it is, it's like you can think of this as 5/16 to the first power, 5/16 to the second power, and perhaps 5/16 to the 0 power, which is 1. So what we have is we have a summation of n squared with its coefficients, and this can go on forever, right? So now, how long is it going to go for? Well, we know what is the upper limit. The upper limit is going to be over here. But actually, what we can try to do is to look at the fact that basically, if we look at n squared times 1 plus this, plus the next one, plus the next one, plus the next one, if we do it plus the infinitieth one, if we don't let the tree finish at all, we recognize that if we factor out the n squared, we have a summation of a geometric series. Because this is 5/16 to the 0, 5/16 to the 1, 5/16 to the 2, etc., etc., etc. We have a geometric series, and this geometric series has a ratio less than 1, which means it's going to converge, which means that the coefficient of n squared is going to converge. So what we have here is, now we take this n squared out of all these terms, and it's going to be 1 plus this coefficient, plus this coefficient, plus all of them. But again, if you take this summation, you guys know all about doing this geometric summation and finding the closed form for it, it will be a constant. So therefore, we will say that the theta of this algorithm will be n squared. Why? Because there is a constant that the coefficients will converge to. Therefore, it's going to be n squared. How do I know it's not going to be more than that or less than that? Because the first one is n squared. So it can't be less than n squared if level 0 is n squared. But what's going on is, what do you think is happening to the work as we're going downward, downward, downward? Is the work increasing across the down the levels, or is it decreasing or staying the same?
Decreasing.
It is decreasing. And how is it decreasing? It's decreasing exponentially. 5/16, I don't know what that is, but 5/15 is a third. So it's very close to a third, a third, a third, a third, a third. So it's exponentially getting smaller. And that's why those coefficients converge, and that's why our theta is n squared. How else are you going to find that? It'll be a lot harder to do it otherwise. This is a beautiful solution using the recursion tree, and we'll use the recursion tree in other cases. Okay, now so we'll come back to the recursion tree, but it's a very powerful technique for very complicated algorithms. And in this case, we were able to find the theta solution. In other times, we might be able to find the little o or the little omega or big O solutions for very complicated algorithms by using some simplifications and using a recursion tree where a closed form solution or a master algorithm solution might not be possible. But now we're going to look at the master method, which is very powerful when the particular algorithm fits into it. So the master method applies to recurrences of the form T of n, that's our input, the size n, is equal to some coefficient times T of n over b plus f of n. Let's break it down. So our time complexity of the algorithm will be a coefficient of the recursion of the problem cut into b pieces so many times, plus f of n. What's f of n? Characterize f of n. F of n is the actual work. What's a t n over b? Recursive work. Recursive work, recursive cost, actual work. So at level 0, how much work is being done? Use it for this algorithm. F of n. Just interestingly enough, if you were to draw a recurrence tree for this algorithm, what would level 1 look like? Because level 0 would be f of n. So now what would level 1 look like? A is at least 1, and is an integer typically. If A was equal to 1, what would level 1 look like?
T of n by n over b.
Okay, it would be f of n over b. But if A was 2, what would level 1 look like? You would have, if A was 2, that means that recursion of T of n would be implemented with 2 times n over b, which means you would have an n over b and another T of n over b, which means you would have 2 branches. So if A was 2 and b was 2, level 0 would be f of n, and level 1 would be f of n over 2, and then another one would be f of n over 2. And then level 2 would look like how many branches?
4.
Each of them being f of
n over 4.
f of n over 4. Okay.
So Professor, what
Yes.
changes from level 0 to level 1?
Well, what changes is that this is the actual cost of level 0, and this is the number of splits into level 1, and this is the input into level 1, which will then be put into this function. Okay? But you'll see, we'll do much more of that. All right, so what we're going to do right now is we're going to look very carefully at so this is the style of algorithm complexity we can solve super easily with the master method. So we're going to do something that looks absolutely crazy. We're going to say compare f of n. What's f of n again?
Actual cost.
Actual work. Good. So you're getting there. compare the actual work at level 0, FYI, right? So it's actual work at level 0 with n to the log b of a, which is like, whoa, 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 n to the log b of a. Just trust me, n to the log b of a. Because if you can evaluate log b of a into a number, you'll get basically a polynomial exponent, n to some power. And what we're going to do is we're going to compare this actual work at level 0 with n to the log b of a, where a is the number of branches and b is the divisor of the size of the problem each time. And when we compare them, we will find if f of n, if the actual work is equal to or is pretty much proportional with, or is pretty much the same as big O of n to the log b of a minus an epsilon, well, that means an epsilon is some positive constant. That means you have to decrease this exponent to make equality. You have to decrease this exponent, and to this exponent, you have to decrease the exponent to make them equal. Which means that this exponent must be, in order for them to be equal, that means this exponent must be bigger than f of n exponent. So we say that n to the log b a minus epsilon is polynomially, it's easy for me to say, polynomially bigger. F of n, this is n to the log b of a minus epsilon, is polynomially bigger, and f of n is polynomially slower, because we had to subtract a positive from this exponent just to make them equal. Keep in mind that in order to get this, so for example, if we were to make them equal here, we would have to multiply this by n to the epsilon to, if we got them n to the epsilon multiplied by that, you would then have a bigger function here, right? So therefore, this is the polynomial difference between the two algorithmic complexities. And so therefore, our solution is going to be that the t of n, this is the end of the analysis actually, t of n, the actual complexity of the algorithm that we studied is theta n to the log b of a. Let me just review it. So if you compare this against that, and you find that this is bigger, then the algorithm has theta of that bigger n to that power. Period. Period. You're done, as long as the algorithm fits into this type of recurrence. Any questions so far? And I will give you the motivation and explanation, but I want you just to see it for now. Yeah?
So how come we are evaluating it to be a polynomial graph or something like that?
Well, we're just assuming right now that we're not necessarily, we're saying that there's a polynomial component to it. So so we're saying polynomially slower or faster based upon the fact that we have f of n. Remember, this is big O now here. So this is not, if I took the big O off, then it's a difference. But we're saying that n to this power is some kind of polynomial. Okay? So we're saying this kind of polynomial we have here, inequality of this, we're able to match it. So we're sort of assuming there's some kind of polynomial similarity here. But you'll see why later. Okay. Now, the second one is a little bit more strange. Again, we have to have this format. And the master method requires everything to that format. So in this case, we're going to, again, compare the actual work with n to the log b of a. And in this case, we're going to notice that f of n, actual work, is equal to theta n log b of a equals n to the log b of a times LGKN. Let me explain that for those just to review. So we know this is n to the log b of a, whatever the heck that is, and we will know very shortly what that is. That is not a magic thing. I didn't just make it up. People at MIT didn't just make it up. Okay? We're going to find out exactly why we're using it, why they're using it. And we're multiplying by LGKN. Now LGKN, somebody explain to me what is LGN?
Natural log.
No, it's log base 2. So LGN is log base 2. But what's LGKN? log
K
base
times
2 of n to the k power. Which means log base 2 of n times log base 2 of n times log base 2 of n, k times. What would be the value of LGKN if k was 0? That would equal to 1 because that would be LG to the 0th power of n, and that would be 1. So therefore, this LGKN, if your actual function does not have an LG in it at all, and by the way, all logs are proportional, so don't get worried about base 2, base 3, base e. If your actual work does not have an LG at all, it's all polynomial, then in this case, assume k is 0. And then you can find equality. So what we're saying is that if that's the case, if we can find that this is true, then these are growing at similar rates, proportional rates. Therefore, the solution, we're done. Analysis is finished. T of n is that the algorithm is theta n to the log b of a times LG of n to the 1 higher power than k. So if k was 0, it's 1. If k was 1, it's 2. It's LGN squared. When I say squared, I mean LGN times LGN. It's not LG of n squared, because that's just 2 LGN. That's why the exponent goes here. It means that you're taking this and you're raising it to the power of that. Okay. All right, so now we go to the third case. And yes?
So the previous one, if k is, like you said, if k is 0, what it fail for that? Because
So now, k will be 0 if your for example, if you find that your algorithm is theta of n to the log b of a. For example, let's make up a number, okay? Let's say b is equal to 2. Let's say b is equal to 2, and a is equal to 8. That means that you are cutting the problem in half for each recursion, and you're doing it how many times? How many branches?
3.
8. So it's 8 times t of n over 2. A is 8, b is 2. So log base 2 of 8 is what?
3.
3. So that means that now if for example your f of n, your actual work, is theta n cubed, then your k is 0. Why? Because your algorithm is theta n cubed. N cubed doesn't have any logs in it, so therefore make k, you can make k whatever you need it to be to do this equality. So if your algorithm, for example, is 3n cubed, that's the actual work, then that's theta of n cubed. So k must be 0. If your actual algorithm is n cubed, LG of n, then this is true for n cubed, k equal to 1. Can you make that equal? Yes, I can. We'll find out what your k had to be. Was it 0, or was it 1, or was it 2? What was it? So whatever it was, you've determined that the algorithms are growing at similar rates, and so therefore t of n is simply going to be n to the log b of a multiplied by the log of n to 1 higher power than it had to be to set the equality. So that means that the smallest value of this exponent in the solution will be 1. Because the smallest value of k in the equality is 0. So it must be 1. It's very interesting. It's like, why the heck does it? Well, you have to have a log. Okay, we're going to find out. Okay, so those are two cases. Third case is very similar case. Now, once we look at the third case, then I'm going to sort of give you an overview of what the heck these cases are doing. So here we have, again, we compare actual work against n to the log b of a. You're probably tired of it. N to the log b of a, n to the log b of a. What we're going to do is we're going to see, is f of n an element of big omega of log base b of a plus epsilon? If that's the case, then I had to bump by epsilon this one, which means if I didn't bump it, it would be too small, and that means that f of n is growing polynomially faster than n log b of a by a factor of n to the epsilon. some positive thing, right? Now, we got to do one small check for this last case. We have to check to see whether the actual function satisfies the regularity condition. Notice it's in red, which means that usually means important. You know, if you see a red sign, it usually means. So regularity condition means that a f of n over b is less than c of f of n. Now, nobody understands what that means, but we have to understand what it means. So now we have to break down what those numbers are really representing. Can I sit over here? I'll let you sit. Are you on your phone? Are you very bored? All right. I'm going to. All right. So, what is f of n over b? Think about it. What is f of n over b? What is b? What are we doing with b? What is b doing? B. Think about the original format of the master algorithm format. T of n is equal to a times t of n over b plus f of n. So, okay, so what's b again?
Into how many pieces of x?
You can give me a better answer than that.
Recursive input is divided by.
Okay, so who gets the input n over b? What level? Let me ask you this.
0.
First level.
0.
Level 1.
Oh, yeah.
How many times?
8 times.
8 times. Okay, so f of n over b. Now who can? Now we know what n over b is. Do you know what f of n over b is?
Actual cost.
Actual cost of level
1.
1 multiplied by the number of those costs at level 1. So this is basically showing us the actual cost across level 1. And we're saying it must be less than or equal to some constant, less than 1, times what?
Actual cost of the algorithm.
Okay, so what we're saying is that level 1 must be what? Decreased over level 0. Okay, so the regularity condition says that the actual work as we go from level to level is definitely
Decreasing.
cannot stay the same. It must be decreasing. Cannot stay the same, must be decreasing.
But less than or equal to is it?
Yes, but constant has to be less than 1. So therefore, if constant is 0.9 and you are equal to 0.9, you're still less than. If the constant is 0.9999999 and you're less than or equal to 0.99999, you're still less than 1. Because the actual cost is 1 times C of n, C of f of n.
Why is it equal to?
Why is it equal to? The reason it's, who can tell me? Who can answer why it's equal to? Why do we have equality? It's a small point, but I'm glad you asked. Who can tell me why is equal to is here?
C is less than.
Because C is forced to make C, because f of n is the actual work at level 0, right? Okay, so if I have any constant less than 1, this will be a little bit less than level 0 work. So that means you can be equal to a little bit less than work or a lot less than that. Does that make sense? So it's always, so it means that the work is decreasing. Always. It's strictly decreasing across the levels.
Does that account for like the first level or level 0?
So whatever it is at level 0, level 1, across all its levels, how many? A of them. Across all its levels, there's going to be less total work in level 1 than there was just in one node of level 0. And this will continue. There'll be a little bit less work. Okay, so let's go back to here because we forgot this. So basically, we are finding here that f of n is polynomially growing faster than n to the log b of a. Therefore, the work is decreasing. That's the regularity condition. Therefore, t of n is theta of f of n. So let's just think about what that said. It says, what's the actual work at level 0?
F of n.
And what's the t of n complexity? Theta. Theta f of n. What we're saying here is that the actual work at level 0 is f of n, and the work is decreasing, therefore we're saying that the actual complexity is theta f of n. We're saying the work across the entire tree, no matter what the value of a and b are, as long as the work is decreasing, is proportional to the root level, which is level 0. How is this work decreasing? How do you think the work is decreasing? It has to be decreasing exponentially. You'll see. Okay, so now let's analyze this. So let's look at an example.
In the regularity condition in the previous slide, why do we need C there? For sure, from level 1
We
is
want-
less than level 0 and level 2 will be less than level 1 for sure. So why do we need, why do we place a C?
1 will be less than 0.
Yes.
Yes.
So why do we need a C there? Constant. Why do we place a constant there?
Well, it's-
Though
we
we
do-
don't place a constant as well.
Hold on a second. Because you agree with me that f of n is the actual work at level 0, right? So this is the actual work. You agree with me that C is less than 1, like 0.9. So therefore you must agree that 0.9 times the actual work is going to be less than what's actually being done at level 0. So that means that the work at level 1 must be no more than equal to less than that at level 0.
Why is the constant not taken over to the first level and second level? Why is it only in the second level?
Why is it only here?
Yeah.
Because what we want to do, we want to show that if you decrease the work at level 0, not actually decrease the work at level 0, if you create an expression that has less work than level 0, it will be, at most, that's what you'll get out of the work across all of level 1. That all of the work in level, this is the actual work at level 1, this is a reduced work at level 0. So the actual work across everything in level 1 will be no more than a reduced amount of the work at level 0. Which means that the work at level 1 across that will be decreasing. Okay, so let's look at this. There's a couple examples we're going to look at here. So what is the value of A? Coefficient of the recursion, right? How many branches does that mean?
4.
4 branches. And then B is how we're dividing the size of the problem, and that's equal to? 2. So n to the log B of A is going to be n to the log 2 of 4. Log base 2 of 4. 2 to what power is 4? 2. So therefore it's going to be n squared. So what's going to happen is n to the log B of A is n squared. Okay? When we finish this, you'll be like, oh, that's so cool. Okay. Not yet. Now you're like, oh, that's so weird. Okay. So n squared is the value of n to the log B of A. F of n is equal to just n. So what's the value of epsilon? What's our epsilon? You can see epsilon is equal to 1 because basically for them to be equal to each other, I would have to have times n to the 1, so epsilon would have to equal to 1 because epsilon is the exponent of n that I have to multiply them for equality. So therefore you can clearly see what is a bigger function, n to the log B of A or f of n? N to the log B of A. Okay, so in that case, we are finished, and T of n is theta n squared. We're done. Which is like, really? Like, yeah, really. We're finished. Okay. Now again, you might say, well, why are we finished? I could draw you a recurrence tree, but I'm not. You can do it yourself. If you drew a recurrence tree, what would it look like? Well, it would have an n here. How many branches?
4.
Okay. 4 branches. Each one would end up, what's the actual work?
N by 2.
N over 2, N over 2, N over 2, N over 2. So first level, we executed with complexity, N. But second level,
N over 2.
And over 2 to the 4.
add them.
4 times.
4
So?
N over 2.
Nobody got it yet? 2n.
2n.
2n. And on the level 2, you'd have n over 4. How many times? 16. So what's the actual work across level 2? 4n. So we start with n, level 0, 2n,
4,
4n. What do you think is next?
8,
8n, 16n. So the work appears to be
exponential.
increasing exponentially. One nice thing about exponential growth, you guys know about the second power tree. So look at this. So look at this. So you have a node, right? You have one node here. We're going to do a binary tree. It's going to be full. So this is going to be like magic. You guys will just. So how many nodes are in this tree with only root?
1.
1. How many are here now?
2.
Total nodes.
3.
3. Now I'm going to go against here.
7.
Total is 7. So 4, 2, 1.
1.
2, 4. Okay. So how many total?
7.
7. If I add another full level, how many nodes are just at that level? 8. So from 7 we add 8, go to 15. At 15 we add one level, we add 16. So what we're doing, think about it, what we're doing is by adding one level, we're almost, or actually more than, but pretty much doubling the total of came before. Okay, so if I have 1,023 nodes in a tree, 1,023, the bottom level has 512 leaves. If I add one more level, it's going to be 1,024 added to it. The whole tree will go to 2,048. I'll double it. I'll double it. Just think about that for a second. Now, what about if the tree is not power 2, but power 4 tree? Or power 3 tree? So I have one node, then I go to what?
3.
Total of
4.
4. And then I'm going to go to how many?
9 plus
9.
4.
So this tree is going to grow.
13.
What's going to happen is as a degree 3 grows, or order 3 tree grows, we're going to go 1, 3, 9, 27, 81, 243, 729. Okay, so what's going to happen is by the time we get to the leaf level, that leaf level alone will have more leaves in it than all the levels that came before. Same as a binary tree. If we have a binary tree that's got 1,023 nodes, 512 at the bottom, those 512 leaves are going to get 1,024. The bottom level will have more nodes in it than the entire tree put together. Which is really pretty amazing, right? Okay, so we'll explain that in a second. So let's look at this other example here. So notice that our A is still 4, our B is still 2, but what has changed? Actual work. F of n is now equal to n squared. Okay, so what difference does it make? The difference that it makes is that when we compare them, we still get n squared for n to the log b of A, but we also get n squared for f of n. So now we find that the two values are equal to each other in the case that f of n, which is this, is equal to theta n squared times Lg of n to the 0 power. That's case 2. That is k is equal to 0, so therefore we're done with our analysis, and the theta, or t of n, is theta of n squared log n. Which is k goes up by 1 from 0 to 1, which is just LGN. Okay, and let's just see what the recursive tree is going to look like. You've got to use your imaginations now. How much work is being done at level 0?
n squared.
Okay, now this next part is going to be very hard. Not really very hard. Okay, how many branches?
4.
Okay, 4 branches, but they're all the same, right? In fact, master method requires all branches to be the same. That's why it's an A times repetition of T of n over B. It's repetitions. So we're going to have n over 2, right? And n over 2 is going to come in and get squared, so it's going to be n squared over
4.
n squared over 4. But how many branches?
4.
So it's going to be, what's 4 times n squared over 4?
N squared.
N squared. Well, what was f of n again?
N squared.
In level 1? N squared. Okay, do we dare go another level? I don't know. I think we should. So n over 2 to level 1, it goes to level 1, and n over 2 divided by 2 goes to level 2. That's n over
4.
n over 4. So that means each of those branches are going to do n over 4 squared, which is n squared over 16. How many branches? How many branches at level 2? 16 times n squared over 16. What's the total work?
N squared.
Okay, what's going on? What's the work doing across the levels?
N squared. Same.
Staying exactly the same. But we're cutting the input by 2 in half. How many times can we go level by level and cut the input in half? Log base 2 of n. So that means for each level we're doing n squared, n squared, n squared, n squared, n squared, but the number of times we can keep doing it until we go to unity is log base 2 of n. And notice that our theta is theta n squared log base 2 of n. So this LGN is simply the fact that the height of the tree, and this is the amount of work per level. That's what this one does. That's what this one does. Okay? The previous one was a little bit different. Okay? Let's go on and to see.
Sometimes this is very unresponsive.
Professor,
Yeah.
for that log function, can't we bring that k power in the front because it's a logarithmic function, right?
Power in the front? No, it has to be right here.
Like a prefix, because in log we can bring the power.
No, because it's not log of n squared. It's log of n squared.
Okay.
That's what I tried to say. When the exponent goes in the middle, it means you're taking this to the power of that. And it's not just the log of this to a power, which then could do, but this is very, very different. Okay. Okay, let's take a look at this one. Notice that our a and b are still the same. Our f of n has now increased to n cubed. Well, guess what's going to happen? In that case, what we're going to get here is that f of n is now outpacing n to the log b of a, which is n squared. Okay? Now, the question is, this is case number 3. We have to make sure what? We have the regularity condition. So the regularity condition says how much work is being done at level 0. N cubed, so we put a c in front of it, okay? C n cubed. And we're going to compare it across all the work at level 1, which is going to be a times n over b cubed. So this is going to be what? This is going to be n cubed over 8, 4 times n cubed over 8, 1/2 n cubed. So, therefore, c could be equal to 1/2, and then we have, so 1/2 is less than 1, so that tells us that the work is definitely decreasing. If we meet the regularity condition that the work is decreasing, then our T of n is simply the actual work at level 0, theta of n cubed. Now let's look at this one. So now, look very carefully why there's an issue of this one. So we have 4 times T of n over 2 plus n squared over LGN. So A is still 4, B is still 2, and our n to the log B of A is still n squared. Our f of n is n squared over LGN. Now, what we want to do is we want to compare f of n against this one. So the master method doesn't apply because for every constant epsilon, which is positive, epsilon always has to be positive, we have n to the epsilon. What does this mean? n to the epsilon will always be greater than, right? This is going to be, is an element of little omega. What does that mean? Lower bound. So n to the epsilon, for any epsilon that's positive, it will be a faster grower than Lg of n. So we cannot find the polynomial faster, slower. So in this case, we cannot find the epsilon. So that's why it doesn't apply. I'm not going to give you that kind of problem. So relax. At least not on a test. Homework? Of course. All right. So let's see.
Professor?
Yes?
The first example, how did you recognize that we need to use case 3 by seeing the question? I mean, by using that we need to use regularity condition.
Oh, I knew it was the case 3 because when I compared f of n against n to the log b of a, I noticed that f of 1 is bigger.
Okay.
It was bigger. Okay? Now, here comes the idea of the master's theorem again. Like, why didn't I think of that? All right, so first of all, you understand that this is the actual work at level 0, whatever it is. Okay, so now a is our coefficient, so that means we have a branches of f of n over b. And then we have n over b, which is n over b squared, right, like this. And eventually, as we keep cutting it by b, we'll get to unity. What's the height of this tree?
Log.
Log base 4.
Log base b.
Log base b.
Log base b. Base b of n. Okay, so what we have is the total work being done at level 0 is f of n. The total work here is a times f of n over b, and here the number of branches goes from 1 to a, then a squared, because each of the a has another a. So we have a times a, which is a squared. A squared, and the work becomes, and the input becomes n over b squared, so it's going to be a squared times f of n over b squared. The height of the tree is log base b of n, which is, you just told me that, right? Because we're going to go to unity with b. So the height of the tree is log base b of n. The number of leaves, listen very carefully, the number of leaves is going to be a to the h. The number of leaves is a to the h, number of leaves. Because we have here 1, right? A to the 0, a to the 1, a squared, a to the h. But h is equal to log b of n. So it's a to the log b of n. That looks mildly familiar. It just happens that if you interchange a and n, as we did in our mathematical lecture, it's a to the log b of n is also equal to n to the log b of a. It's the same. Because if you take the logs of both of these, with a power rule of logs, you're going to find equality. So therefore, n to the log b of a is equal to a to the log b of n. And what is a to the log b of n? It is the number of leaves, each of which has what input size?
N.
N by b.
Unity.
N by b to the h.
Unity, because once we get to the leaf level, we have unity. That's why it's the leaf level. We can't cut it in half anymore. We can't cut it in 3 anymore. We can't cut it in 4 anymore. So when we compare f of n against n to the log b of a, we're comparing one node doing entire work against all of the leaf nodes doing unity work. We're counting the amount of work done at the leaf level against the amount of work being done at the root level. So if that work is increasing exponentially, then the work being done at the leaf level will encompass everything up to that point, and the theta will be just the leaves. So therefore, if we notice that n to the log b of a is bigger than f of n, that means the work is increasing, and if it's increasing exponentially, then it's going to be theta of this. If we notice that f of n is larger than n to the log b of a, that means the work is decreasing exponentially, which means all the work will be proportional to the root level, which is level 0. If we notice the work is staying the same, then it will be the same times log b of n. Let's see how much time we have, because I could give you something small here, but I think. Oh, we got a little time. Excellent. Okay, I don't know why I'm throwing that. Okay, so let me show, I just have a little bit, let me just throw in an extra, so these are some extra notes that I have here. Okay, so these are my notes to complement those book notes that we just looked at. So we have seen that the master theorem for any function in the form of this, you start at the root, split the recursion into a branches, blah, blah, blah. We've seen that already. We note that everybody understands a to the log b of n is n to the log b of a. And if you don't, go back to the mathematical lecture notes when we deal with logs. It's a lot of fun. Just take the log of both sides and you'll see that they are the same, because one of them is an exponent, which is a log, comes out as a factor. So the factor and the exponent both become factors, and that's what makes an equality. Okay, so what I have here, let's see if I can make it any bigger. I doubt it. Not really. It's not really any better. Okay, so if we have this case, okay, so a is 4, b is 2, f of n is equal to n, and n to the log b of a is equal to n squared. Now look very carefully what I have here. So what I'm showing you here is I'm looking at the fact that the number of leaf nodes is n squared. That means the leaf nodes are doing together n squared work. There's only one root node and it's doing n work. So that means we start with n work, we're increasing, and we're finishing with n squared on the bottom. Okay? So in this case, f of n is equal to n, and if you expand the tree, you get 4n over 2, which is 2n. We did this before. Then we have 16n over 4, which is 4n. Then we have 64n over 8, which is 8n. And we go up to n squared. Notice that we have essentially 1, 2, 4, 8, 16, all the way up to n. So therefore, the cost is increasing geometrically on each level, which means that the total work is proportional to the work just at the leaf level. In this case, we have n squared. So we notice if it's n squared, if you draw the tree, you're going to get n squared for the leaf level. Then we did this before, 4 times n squared over 4, which is n squared. N squared, it just seems to, the coefficient here and the divisors here are balancing out. You always get n squared. So therefore, the work is always the same. How many times do you do this? You do it at the height of the tree, which is log base b of n. And in this case, we have n cubed. So n cubed is growing faster. So that means we do more work in level 0 than there are leaf nodes. And the leaf nodes do unity work. So therefore, since they're n squared unity work, it's n squared total work at the leaf level. So we are decreasing. As long as we have the regularity condition, we're going to see what's going to happen here. So we do n cubed in the first one. Then we do 4 times n cubed over 8, which is n cubed over 2. Then we have n cubed over 4, n cubed over 8. And eventually, we get down to n squared. We keep decreasing it until this increases all the way up to n. And we have n cubed over n, which is n squared. So the cost is decreasing. How? Exponentially. And so therefore, the work, all of the work, will be proportional to just the leaf level. Does that make sense? Okay, so it's important to understand, I'll just spend a couple of minutes, it's important to understand that when we use the master theorem, we understand what it's good for and what it's not good for. Always you test the regularity condition if the work is If the work is what?
Greater at root node. It is, if it is
Less
decreasing.
than work at
If-
0.
If the work is, if the number of leaf nodes
It's greater than
when do we have to check the regularity condition? When the work, we want to make sure the work is
Decreasing.
decreasing, which means that f of n is what?
Greater than.
Greater than n to the log b of a. Then you want to make sure there's a regularity condition. If there is, you're done. All right, so let's see if I can show you. Oops, I can't do this one. So let's say we have this following example. Let's say we have t of n is equal to oh. Actually, I don't care. That's strange. Maybe I look at it the wrong way.
Can we do 9 times 8 and then
Hold on. We're going to do the other way around. Yeah. Now remember, LG proportional to any other log, right? So what's the value of A?
3,
A is equal to 3. What's the value of B?
9.
Is equal to 9. So f of n is equal to,
N log n.
so I'm going to say n L G n, right? And then we have n to the log, oh, I don't want to do that. That's what I want to do, sorry. 9 and 3. N to the log b of 9. So what do we have here?
N cube.
No. Yes. Yes. So no, not n cubed.
N square.
N squared. You guys are gonna mess me up. You're doing it on purpose. Yeah, okay, thank you. 3 to what power is equal to 9? 2. So this is going to equal to n squared. Okay. So how many leaf nodes are there?
N square.
Okay. So it appears that the work is increasing. Okay. Let's just see if we can. So we can solve this. Can we solve this with the master algorithm?
Yes.
Okay, let's try to do it with the recurrence tree. So we have n, l, g, n, right? So now how many branches are we going to have?
3.
9 branches. So I'm going to say 9 times. Because I'm not going to draw them all, right? Because if you want me to draw them all, I'm just not going to do it. Okay, so each one is going to get what? What's the input?
N by
N by 3.
So it's going to be, we'll just write n over 3 goes in for n. So the actual work being done, so, and then for the next level, what is it going to be? N over 3 over 3, which is going to be n over 9 for the next one.
20. N over 20.
N over 27, okay. That's just what's going to happen. This is going to be times what?
9.
So we have 9 branches here, and we're going to split 9 again.
8.
So we're going to have 81, and times 9 again. 729 times, right? So these are our coefficients, these are replications here, right? So can we even do, so now let's replace this n cubed, and then, so this is the input size, but the actual work is going to be n over 3 times lg of n over 3. That's the work. I'm going to underline the work, right? And here's going to be what?
N over 9.
It's going to be n over 9 times lg
N over.
of n over 9. That's the work. And here we're going to get n over 27 times lg of n over 27. There's going to be 729 of these things. This is going to be, what's 729 divided by 3? Actually, no. Okay, let's just think of it like that for a second. So what is this work? Let's just simplify this work. So this is n over 3. What's LG of n over 3? How do you simplify LG of n over 3? LG of n minus LG of 3. Oh yeah. And we're going to multiply this by 81. So we're going to be 81. So that's the actual work at level
Yeah.
1.
One.
So this one is going to be 729 times n over 9 times LG of n minus LG of 9. And at level 3, we're going to have set. Am I messing this up? This is 9. This is 9, right? This should be 9. I'm a mistake because we're getting 9 here. This is going to be 81. Sorry, guys. And this finally will be 729 times n over 27 times LG n minus LG 27. Okay, so what is this over here? This is 9 times n over 3. What's that? So that's going to be 3n LG n minus LG 3, right? And what's 81 over 9? 9n times LG n minus LG 9. And this, I'm guessing, might be...
27.
So what's 729 divided by 27?
27.
27n times LGn minus LG 27. So, what does this work appear to be doing? So, what do we have here? We have our f of n is here, and this is our, so the work appears to be increasing. How? Appears to be absolutely exponentially increasing. Now what is LGN? Notice that LGN is a constant, right?
Yeah.
So what we have here is really, this is, let's simplify this again. This is going to be 3n LGN, right? Minus 3n times LG3 is equal to 9n LGN minus 9n LG9, and this last one is going to be 27n LGN minus 27n LG27. Now, so what is LG3? I don't know what it is, but how does it compare to LG3 and LG9 and LG27? What's happening here? It's increasing. This is increasing. And what about 3n, 9n, 27n? It's also increasing. How is it increasing? Is it increasing exponentially? Well, this is increasing exponentially, but this is
Increasing back now.
this is also, so this is increasing and this is increasing, right? They're both increasing, so this whole thing is increasing, so we're subtracting more and more. And what about this part right here? This is increasing exponentially. Okay, so what does the master algorithm says for us? So let's compare, let's find the epsilon. So we have f of n is n L G n. And then we're going to have n squared, right? Now, we want to basically set this up for equality. Can we set it up for equality? Is there any n to the f? Which one is going more quickly right now? Right or left side? Right side, left side? Right side is growing more quickly, right? So now, so I'm going to have to try to find out where I can have. So right now, can I have it so that it's going to be less than or equal to? Is there an epsilon here? Is there an epsilon that I can use for E that would make it less than or equal to? This is n times n to the epsilon. What am I trying to find? I mean, if I can find the epsilon, what does it mean? What does it mean if I find an epsilon? That's the question. That's that hard word that I couldn't pronounce. If I can find an epsilon that makes this true, then I will recognize the fact that f of n is polynomially smaller for a positive epsilon. So what about if epsilon was equal to 0.000001? Then this would be n to the 1.00000001 times LGN. Would that be less than n squared always, polynomially?
Yes.
Yes, it would be slower. So therefore, there is an epsilon. So that means that we can use the master theorem to say that this T of n is an element of what? Theta of
N squared.
n squared. Done. How much work is being done at the bottom level? So in this case, the recurrence tree is difficult to deal with. Not impossible, but difficult to deal with. We can try to simplify it. But clearly, this is a very easy solution once we can find out the fact that this is growing more quickly, this is smaller, and then we can do the comparison. Okay. See you guys next week. You guys, the homework.